It's our greatest pleasure to have with us Arianna Bisazza from the University of Groningen, who's today going to be talking about like the first NLP application that we have for the summer school, which is going to be machine translation. And without further ado, the floor is yours.
Hi, good morning. I'm Arianna Bisazza. Thanks for being here on Monday morning. And to follow up on what Yannis just said, the beach is really great. I can confirm that. So if you have time before you go back to your not so sunny countries, do go to the beach. And yes, so today we're going to talk about machine translation. Yes, so let's get started. Of course, feel free to interrupt anytime if you have intermediate questions. So this is a website in English that it's talking about the city where I just moved, which is Groningen in the Netherlands. And I invite you to give a quick read and see if there's anything wrong with this text. Maybe you can just jump to the second part, give you a little hint. Are there any English native speakers? Okay, so you should be the first to notice something strange, maybe. Sorry? Can you repeat? It says shop fence, okay. I didn't even see that one. So I found really little disfluencies in the second part. For instance, there's the local neighborhood pub, which I think should be pubs. And the very last line doesn't sound really like proper written English. Not only in the pub, by the way, and then there is a period. Anyway, I don't know if you get where I'm going through. So this is translated from Dutch. And I think it's pretty great. Like, really, I don't know how long you have been in NLP, but this quality of machine translation used to be so much worse. You could immediately understand that it wasn't fluent. And of course, this is that Dutch English, so we could kind of put it in a category of easier language pair, although it's not the easiest one, but these two languages are clearly related to some extent. But still, this is just to give you an idea, and it's good to stop for a moment and realize that this field has done a really huge jump in quality, thanks to the neural methods. So we are in 2019. Machine translation is a pervasive and, well, reliable technology. I couldn't resist to put the usual joke. I think this is pre-neural, but I don't think it would do much better now because the problem here is the lack of context and, yeah, maybe not a lot of similar training samples in the training set. It used to be easier to make this kind of jokes before neural MT, unfortunately. Now don't get that much fun anymore. But anyway, so you know, there's the quality of online systems is pretty high for many language pairs, not all. So I won't go a lot into talking about this topic today. But for many language pairs where there is a good amount of training data, the quality is pretty satisfactory. And also, it is an important part of professional translation workflow. So it's not only for like browsing users that don't have a really high demand in quality. Actually, MT can also be used now by professional translators. The typical workflow in a lot of places is actually you have first the neural machine translation translates a sentence, and then it's followed by post-editing. And because neural machine translation has become so good, it can actually be part of the workflow most of the time, whereas before you had all this issue of is actually the input of the MT going to disturb the translator. So MT is a core problem of NLP. It has a long history and variety of approaches, so I think it was a good choice to put it as the first NLP application in the summer school. And so we can just recap what are the main families of approaches to MT. The first and oldest is rule-based, where the idea very briefly was to manually create bilingual lexicons and then a bunch of parsing and translation rules. There is a lot of approaches there. And of course, this tended to be rather precise, but the recall was a big problem. How do you cover the largeness, the whole variety of translation phenomena that can happen in a language pair? And also, how do you cover their lexicon properly? Then there was a long time where we used statistical MT method. Well, we could say that we still are with neural MT, but this is, I will talk about SMT as pre-neural SMT during the rest of the talk. And these were mostly based on information theory principles. We are going to talk more about this today. And finally, neural MT, which is really very young approach, which is a conditional language model based on deep neural networks. So yeah, to situate a bit all of this in the history, I think it's good to go through a timeline of this kind. So we are going to be talking mostly about neural MT, and that's probably all you're gonna deal with if you are going to start a PhD now in the field of MT. But this is really recent, as I said. So the first really working approach to neural MT was only dates from 2014. And the things moved very quickly. So in a couple of years, this new approach was already beating phrase-based SMT, which had been around for a very long time. And it became adopted by large online MT products. And in 2017, we had this new approach, Transformer, which we are going to talk in detail also about today, which also replaced the previous type of architecture based on RNNs and became the new state of the art. So what you see, what is behind the large system on lines is mostly Transformer nowadays. So, but let's go back in time. So this is a very typical way to start an MT lecture. So there is this important date, which is the 1947, and this famous memorandum that was written by one of the pioneers of statistical MT, which is Warren Weaver. He said a bunch of different things in this memorandum, but two that I like to recall here is that he actually already at that time framed MT as a code deciphering problem. And of course, it was a time where cryptography was really important. They were trying to break codes, the Russian secret codes. So this actually brought some ideas also to the field of NLP. And it also highlighted limitations of early approaches that were only looking at word-by-word translation equivalencies. So he really saw things quite ahead of time. Then let's jump to the 90s. So it took quite a bit of time to actually for the first working SMT systems to appear, and these were mainly developed in the IBM labs. They were based on the noisy channel formulation. We are going to talk a bit more about that in a moment. And they were tightly connected to advances in speech recognition. So while you can think that neural MT has been inspired a lot from techniques in the computer vision field, the techniques of the first statistical machine translation systems were more inspired by advances in speech recognition. This is something that not a lot of people know, but I like to put it also on the timeline. In 97, actually, there were two papers proposed by two Spanish groups, one in Alicante and in Valencia, that actually already in 97 had their first they outlined the first approaches to do neural machine translation, which they actually called connectionist MT back then. And they were strikingly similar to what we are using today, but they couldn't really scale back then, so the field was not ready to get this really working. So they were abandoned and largely forgotten until I think Kyung-Gyun Cho did some research and he found them and made them famous again. And then you have the 2000s. So 2000s are the years where SMT becomes really established and adopted also in the real world. And there are multiple advances done. There is, concerning phrase-based SMT, there was a lot of development and research going on around this open source platform, Moses, which you could have heard about. But there were also parallel advances in related subfields, so syntax-based SMT, which exploits parsers to bridge across languages. This was also a very productive research field. And tree-based SMT is, well, also syntax-based is a type of tree-based SMT, but it requires a parser to work, whereas tree-based SMT was working by, in a completely data-driven way, by by learning synchronous grammars directly from parallel data. So that's all we need to know for now about this family of approaches, but it's good to know that there's a larger picture beyond NMT. And so this brings me to today's lecture. So what are we going to talk about today? We are going to spend, some time about pre-neural neural machine translation, so phrase-based SMT. Then the core part is going to be about the the main architecture of neural machine translation. So RNN-based sex-to-sex is basically what Barbara has explained 2 days ago, but we're going to go through it again, make sure that that everyone has understood it. The same sequence plus attention, and then transformer, which is a non-recurrent, fully attentional network that also does sequence-to-sequence prediction. And there are also some other topics, if we have time, that I would like to cover, even if very briefly, but it's important to be aware of these things. So how is decoding done in neural MT? How are words segmented? What are different ways to segment words as a pre-processing? Then we should talk a little bit about evaluation, because that's also very important. I don't think anybody has really covered that so far. And finally, some time to discuss open issues in this field. So let's get started, unless you have any questions so far. No? Okay, great. All right, phrase-based SMT. So why a lecture on phrase-based SMT in 2018? I have a couple of reasons. History is fun. And Greek like history, so some Greek here asked me to do this specifically, and maybe they were right, because after all, this is not so long ago. So maybe there's still something that we can learn from this family of methods. And I think that MT history can give us a good grasp of how the NLP field has been transformed in general in the last years. So some fundamentals of statistical MT, so this is even before phrase-based actually. So the early SMT approaches adopted the noisy channel model, which was directly borrowed from cryptography field actually. So you have this idea that there is an original message which was uttered in English, you don't observe that, and it was corrupted or encoded by some also hidden source, the noise source. And this led to a foreign or distorted message output. And what you want to do when you translate, you actually want to recover E. You want to find the optimal, let's call E star translation, which is the best that you can do to recover the original message E. So these are some equations that are really super important in the field of SMT. When you translate, you're looking at the E that maximizes the probability of E given F, so simple in probabilistic term, but you don't have a way to directly estimate the probability of E given F. Otherwise, it will be too easy. So you use a workaround. You actually apply these Bayes rules, which allows you to re-express this conditional probability in terms of P of F given E times P of E divided by P of F. So why is this useful? Because, well, at least in the cryptography scenario, we have a way to, we don't have a way to estimate P of E given F, but we can estimate the probability of the distorted message given the original message, and we can also estimate the probability of the original language in general. So we can have a prior of what the E should look like. And because we are maximizing over E, then we can actually get rid of this P of F in the denominator, and this is really the crucial equation that you're left with. And this gives us the translation model and the target language model. So these were the early approaches to SMT. And if, of course, if you factorize this at the level of words, you get a pretty simple model that will not work well in any cases, but it's good to have this in mind as the framework. So what happened in the late in the year 2000s, we moved to a discriminative approach, and we also moved to a phrase-based translation models. So instead of modeling word-to-word equivalencies, we were modeling phrases, which seemed already like a huge advance. And this method, what allows you to do, it allows you to combine an arbitrary number of feature functions, so it's more flexible than the previous one. And it also introduces a hidden variable, which is the phrase alignment. So this is an added complexity because you have many ways to segment the sentence into phrases and to reorder them. And here phrases are actually, you can think of it like n-grams. They don't need to have a linguistic grounding at all. This is the equation that is important to have seen at least once. So we are again looking for the E that maximizes this quantity, but we are also looking for the phrase alignment that maximizes this quantity. This quantity is the combination of a bunch of functions that are defined over the source, F, the target E, and the alignment variable. So what could be possible candidates for these functions? So what all the phrase-based models back then had were phrase translation probabilities in both directions. Why not? Because you're not constrained to any probabilistic form like we had before. You can do also, again, word translation probabilities. And you basically just get this by counting. I will show you an example in a moment because this is still very abstract. You can have reordering models. So before Neural MT appeared, I wrote a very long surveys on word reordering models, and then this thing became completely obsolete, but there was a whole subfield of research around trying to get the reordering right. It's pretty interesting to think about it today. And also what this new formulation allows you to do, it allows you to weigh the importance of each of these submodels or features by tuning them directly to maximize a measure of accuracy of translation on a development set. So you can automatically find which models are more or less important for your task. So with this framework, we got pretty good, what we thought was pretty good machine translation quality back then with a fully data-driven approach. And this is what the whole, the complete framework look like. So, well, some of things we still have now, but some are quite different. So it's good to look at it again. So we had a bunch of documents in source and target language that are aligned at both at the level of document and at the level of the sentence. And then you use them to extract a bunch of statistics. So we talk about the phrase translation model, which could gather counts of how often a given F phrase occurs aligned to an E phrase. Reordering model, so how often a given phrase gets reordered in a certain way in the target sentence. And you can think of many other models here. And then separately, this was something that was pretty nice and easy to do. We could incorporate a lot of monolingual target data with this P of E. So you could build a very large n-gram language model on a lot of data that you have, and you could incorporate it easily in this framework. What do this model actually look like? They are count-based, as I said, maybe with some simple smoothing. So you go through the text and you find that, oh, sorry, I forgot something important. Before training a phrase translation model, you need to do also word alignment. And that's a whole bunch of other techniques that allow you to do word alignment automatically. Once you have that, you do phrase extraction, and then you count how often a phrase is translated as follows. So you have, for instance, freedom could be translated by all these different phrases with the given probability. I switched to another language pair, by the way. And let's see, this is a particular type of reordering model that you have. So here you estimated the probability of translating. So let's say we have seen the phrase free, and we have estimated the probability of translating this phrase after the previous source phrase, or after the previous, after the following source phrase, or any other reordering. So you are building the translation phrase by phrase, and this gives you probability of how these phrases should be reordered in the context. And finally, the language model. Well, this maybe is what is mostly similar to what we are still using today as language models, but of course, this was n-gram based, so that meant two enormous limitations. One, that you have the Markov assumption, so dependencies are always bounded to the previous n words. This was a really hard problem to solve, because you couldn't just increase the n and look at more history. Well, you could, but then your count would become so sparse that it wouldn't really help to have such a model. So most of the time where you had enough data, we were using 5 grams back then, phrase-based SMT. And yeah, the other very big limitation is that all these counts, this is something that maybe is perhaps the most important thing to realize about this earlier method, that you were counting over atomic units. So each word or each phrase is an atomic unit. The phrase free doesn't share anything with the phrase freedom in terms of parameter. And that was obviously a very bad way to make use of the data, but we didn't know how to do it back then. And of course, with the neural methods, you get all these continuous representations that allow you to share parameters and information between words that are similar, occur in similar contexts. Okay, so going back to the general overview, we have seen basically what was being done at training, and now we have the test part. So we have our decoder, which makes the combination of the submodels that you have trained using the equation that we have seen before. And I think that's all I wanted to say about training and test. Yeah, so maybe you see now why I chose this picture. I think it's a pretty good way to depict a phrase-based now, looking back. It had all the pieces that it needed, but yeah, they weren't really working so well with each other, and each had their own very heavy limitations, a lot of independence assumption. So that's what we got back then. So how were we doing testing also, a bit more in detail? This is a bit closer to what we have today perhaps, but it has this phrase segmentation bit. So we have at translation time, we have our models that are trained, and we are searching for the most probable translation according to the learned models. So let's imagine this is your input sentence in English. Freedom of movement must be encouraged while ensuring that. So it was a pretty hard search problem to solve, because we had to try at the same time a bunch of different phrase segmentations, a bunch of different reorderings, and for each of the phrases that we were segmenting, we had to look for the best translation in the particular context. So this animation shows you a particular decoding path, but there were actually, you would be looking over a lot of decoding paths at the same time in a beam search procedure. So you might, for instance, choose that must be encouraged should be translated as a whole. And at that point, there's several models that fire. There is the reordering model telling you how likely it was to first translate this particular phrase. And you have translation model scores that tell you how likely it was to choose this particular translation for the phrase must be encouraged. And you have language model scores. Then you repeat, and for instance, you decide to go back and translate the phrase freedom of movement. So you see you're always constructing the translation from left to right, and you have language model scores that accumulate. And you proceed, and of course, you cannot search through all the space of translation, segmentation, and reorderings. So you have approximate search methods to find a good translation according to all your models. So any question about this bit? Yeah, we have one question there. Sorry, can you repeat? Yes, what is the question?
How the model works.
Yeah, so
more formal definition of A, perhaps.
In fact, I didn't go in detail there because there were really tens and tens of them. But one particular, well, the simplest one is not even a model; it's actually a distortion score, and it's telling you, it's giving you a penalty if you jump too much among phrases. So in this case, the first jump could count, let's say, +3 because you jumped 3 words. You see, when you go from the beginning to must, you jump 3 words. So this penalty is encouraging to translate what is called monotonically. So you have less penalty if you translate everything from left to right. And of course, this doesn't make much sense in a lot of language pairs where you do have a lot of reordering. Then the more sophisticated model would actually make this, will actually learn probabilities of reordering based on the content of the phrase. So for instance, again, with this example, we could have a model that tells you how likely that must be encouraged is translated after jumping what's before, really in rough words. And then how likely it is that freedom of movement is translated after having translated the following source phrase. Does it make sense? This is one particular type of reordering models, but you can have many different ways to reorder. Really, a lot of people tried putting also syntactic features or doing it at the word level, learning discriminative classifiers to find out the best position of the word in the target source. So it was really perhaps the most important subproblem of SMT. Yeah. Yeah, one more question there.
How do you get the starting point of the search? Like a simple word-to-word translation or something else? Where do you start?
You mean where do I start? Why I decided to first translate must be encouraged, or where I got the actually target words there?
Yeah, in general, you need to search over the space of sentences and
yeah.
Where do you start and how do you combine? How do you get these fragments, these phrases that you will be combining?
All the building blocks are here. So your universe is given by the phrase table, your universe of translation, which is the one on the left. So you can translate only source phrases that match this big phrase table, and you can only translate them with one of the target phrases that correspond to that. So that's why that phrase has to be pretty big. Does that reply to your question? Yes? Does it sound strange? Yeah. Okay. Any other question? No. Okay, so we move on. So I have only one slide about the other approaches to preneural SMT. For the sake of completeness, I will mention them briefly. Well, actually, before that, let me introduce this Aqua Triangle, which is also a very important concept for MT. So we talked about Warren Weaver, but there is also a very important French pioneer of MT. He was called Bernard Vauquois. And he was mostly working with rule-based MT, and he came up with this diagram to place different MT approaches in this triangle. So basically what you have here is, on the left you have the source language, and on the right you have the target language. So you have analysis and you have generation. So I think this diagram is still very relevant today. And you can transform, or you can how should I say? Well, you can translate at different levels your sentence. So you can remain at a very shallow level, which is what we just basically looked at. So you just look at correspondences of lexical items or lexical short sequences of words. Or you could do a bit more up, and you can also do some morphological analysis. And then from some morphological representation of your sentence, you could do generation. So this would imply that you have a way to do morphological analysis and morphological generation, which in rule-based terms was all based on human curated resources. You could go also to the way of syntax, semantics, and pragmatic, and finally reach this holy grail of interlingua, which was also something that people tried. They tried to develop some sort of abstract languages that would allow you to describe meaning in a completely language-independent way. And then you would have, if you have a way to analyze your input sentence into this format, then you could generate it in the target language. And the interlingua would be universal, but nobody, as you can imagine, actually managed to do this in a very good way. But so why did I bring that up? Because we can use this triangle to situate different approaches. So we have talked about the phrase base, and I like to put it there. So it's not really dealing with any morphological or syntactic analysis or generation. It's just putting together pieces or a little sequence of words that it has seen in the training data. But you also had a lot of research in other SMT approaches. The hierarchical phrase-based one is the one that learns grammar, asynchronous grammar over the parallel data. So I depicted with these two yellow arrows because it's kind of learning of syntax description that is that can work for both the languages. And it worked pretty well, actually. It was competitive with phrase-based SMT. And the way it looks like, without going into details, one translation rule could look like this one. So you have must be translated into a necessario, and then you have x2 and x1. So what this does, it's basically a more advanced version of a phrase, because it also has these placeholders that can match with other phrases and can be reordered. So your translation rules, they are not just telling you how you should translate a specific continuous sequence of words, they're also telling you how to reorder some phrases in that context. Well, I leave it there. If you're interested, you can find this online. And syntax base is very related. It uses almost the same mechanisms, but it requires an already trained parser. So it requires some kind of syntactic analysis that is based on linguistic formalism. So there are a bunch of different models, but one could look like this. We have the parser for the source language, and we use it to constrain the rules that we can apply, the phrases that we can apply to translate. So our phrase or our translation rule could look like must be. So we had must be x2, x1, and now we have must be translated into a necessario of VP. So you cannot match any sequence of words there. You have to match verb phrase. You can also have syntax on the target side, and that would actually have another purpose that would encourage the construction of more fluent and grammatical sentences on the target. But let's leave it there for now if nobody has a question on this. So it's time to move on to neural machine translation. All right, so let's move to neural MT. So I take the same slides that I had before to show you the differences, so to show you how the whole pipeline changed very abruptly with the introduction of NMT. because we basically stopped doing all of these things together. So we stopped coming up with new submodels, which you could also call feature engineering. So different ways to collect different kinds of information from the parallel data. We also largely stopped to train separate language models on the target language, a large monolingual target language, because now we have one model. It's the conditional language model that Barbara has introduced 2 days ago. It's trained end-to-end, and it's based on a neural network, which is really nice. It's not that nobody had thought about this. It's just that nobody could ever get anything like this to work, really. And finally it did. So this is also how the test time changed. So you get rid of this equation because you only have one model. And when you translate, you're looking simply for the E, for the target sentence that maximizes the probability of E given F. So no more combination of features, submodels, and no feature engineering. These two things are related, of course, because if you have a deep enough architecture and you train it you build it and train it in the right way, it will learn the translation features by itself. And this is really a big paradigm change. Questions here? So how does this even work? So this first slide is meant also for people that are really new to this, so forgive me, but it's just good to go through it again, I think, to see how the things change. So what is a sequence-to-sequence network or neural MT model? We have two components. One is the encoder, which is projecting the input sentence, so a sequence of symbols, discrete symbols, into a continuous space representation. And then we have a decoder, which is generating the target sentence word by word from this continuous representation. But what's this? So we know it's a vector of real numbers with an obscure meaning. My mother the other day really said, is it some kind of traffic light? So it's not so easy to explain this to the layman. It used to be much easier before neural MT. And the way you can think about this, I think it's good to very briefly go to this, because it's doing something very similar essentially to what Word2Vec is doing. It's just trying to come up with a long set of features, numerical features, that can describe this sentence. This is about Word2Vec. You all know how this works, so I will not go through this. But essentially, we want a way to do this for a sentence, which is more complex, of course. And that's why we have to recur to more complex architecture, because we have seen with Barbara the earlier ways to do sequence to sequence didn't use the recurrent neural network, and they were not they weren't working really well. So we are going to talk about the recurrent neural network based sequence to sequence as a recap. So we are going to open these two black boxes. The first, the encoder. That's another view of the same thing you have seen on Saturday. So you have a one hot vector input for each word. This is basically just only one feature is firing through the whole vocabulary to denote this is the word that I have at this input. This is mapped to a continuous word representation. And finally, this is fed into a recurrent hidden state. So every time you see this here, this is doing basically the same operation, but with different input. So we have the same, the matrix of hidden to hidden weights is shared at each time step. But of course, the input is different at each time step, and the previous state is different at each time step, so it will give you a different output. You can also see each of the state as a representation of this bit of the sentence, this piece of the sentence we have fed to the model so far. And therefore, the last hidden state encodes continuous space representation of the whole sentence. Of course, this vanilla recurrent encoder doesn't work very well. But still, the early NMT models, they were doing just this. They were only running from left to right, and they were only pasting this guy at the beginning of decoding there, and you could already get some nice translations, but it didn't scale to longer sentences. That was the problem, mainly. Okay, so yeah, I think I put the equations there because they are directly from the Badanau paper, so it could be a good reference if you want to go through the paper again and put the things, link the things together, but we don't need to repeat them right now. But let's see what the decoder is doing. Again, let me see, how am I doing with time? Yeah. So what is decoder doing? So in this particular architecture, as I said, we start with, so the whole target language model is only conditioned on this particular vector, which is supposed to encode everything that it has seen from the beginning of the sentence up to here. You copy it there, or you can maybe transform it using some other method, but let's say it could be just copied there. And then you start outputting target words. Okay. So you will actually get an output word probability at each time step, which, if you are at training time, you can compare with the goal translation that should have been there. So if you are at training time, this is your goal label, and you can compare it, you get an error signal, and you backpropagate, and you update your weights. Or if you are at test time, so your model is trained, you can use it to do beam search, and you can pick, for instance, the one best, the word with the one with the highest probability that's coming out of this prediction, and you can output it there. And then what you're going to do, you're going to feed this word as the input to the next time step. So, yeah, question? So I cannot hear very well. Maybe there's a microphone coming.
Hi, sorry. In this kind of model, what determines the length of the translation? So the decoder does the first word, and then it continues.
So you mean when you are actually producing the translation at test time? How do you know when to stop?
Yeah, or even at train.
Okay,
you know,
so
like
that's good. So I will again highlight the difference between training and test time, perhaps. So now let's imagine we are at training time. For simplicity, only training time. So the whole target sequence is given. So I didn't write it all because it didn't fit in the slide, but you would have a sentence, let's say, of 8 words. So so that's given. And you have also an end of sentence symbol, so you are also learning to output the end of sentence symbol. So this is what's happening. Again, I repeat, at training time, you have an output word probability. You compare it with the actual word, one hot vector representation of the word that should have been there, and then you feed this particular word to the next hidden step. So you feed the gold translation of that word. So there is no exploration, let me call it this way here. You just actually forcing the model in a way to produce word by word what is in the translation, in the parallel data. Okay. Okay, now let's move on to the test. So the test is different, of course, because we want to generate a whole sequence. That's why often people talk about a mismatch between training and test condition. Because when you do test, you need to build a sequence. So you would choose this word. You would feed this, the word that you have sampled, that you have chosen as your optimal translation, to the next step. So this is not the gold anymore. This is whatever you have created so far. And at that point, your model will also, hopefully, decide to output an end of sentence symbol. And of course, there is a trick to, if that doesn't happen, you can just say, okay, the maximum length is this, or a bit more involved. What usually have in the decoder, you have some penalty based on the ratio of the length. So it's a very, very simple way to encourage the decoder to produce a sentence that is more or less of the same length as the input sentence. Is that clear? Okay, perfect. Yeah.
I realize that there are different approaches to this, but I'm asking about the general case, let's say. You said that at the training phase, each time our network produces an output word, it is replaced. We also take into account the target phrase, so we feed the network with the target phrase instead of just the produced phrase. Is that the produced word? Is that
okay. So maybe because I mentioned this mismatch between training and test, is that related to that?
No, it's. I'd like to ask if
there are alternative ways to do that. To train? No. Sorry.
Just to make clear something, because I'm a bit new to RNN in general.
Yeah.
So maybe this is classified as an RNN question. So, do we take into account when training, with one training example, do we take into account the target phrase at the end of when the whole phrase, when the whole sentence is translated? So do we do the correction phase after the whole sentence has been outputted, or do we take into account the target phrase in each step?
In each step.
But
yes.
When does the backpropagation take place?
It takes place for all the time steps. So you learn, you have an error, you have a cost function at each time step. You can also do it, you can accumulate it and do it at once. But actually, that's the thing with recurrency. You have to unroll it through time. So what you have to do, you have to, you get the error for the first word, then you feed that to the second one. Oh. You get the error for the second one, you feed it to the third. And actually, when you are at training time, because you already know what the whole sequence will look like, you can actually do that at the same time for all the time steps. But this is more of an implementation thing. It doesn't matter for what you're doing. What you're doing, I think it's easier to think about it this way. You learn the error for your first predicted output word probability. Then you input what should have been the correct word to the next hidden state. You do the forward pass, you get a new output word probability, and you do the same thing with the second word of the gold translation.
Thank you very much for the detailed description.
Okay. No problem. So at the end of the day, you have done this for the whole sequence, but you have done it step by step, yeah. And maybe also related to that question, that's something also important to notice. So there are two differences with the test. Well, it's one difference, but it has two implications. So the first difference is that is more of a computational one. You need to wait to have produced this word. So now this word will not be just given by the parallel data. You are choosing it from this probability. You need to wait for this word to be generated to go to the second step. and you need for the second word to be generated before you go to the third step, because you're doing it on the fly. And the implication here is you cannot parallelize much. So this becomes inference can be really slow. It's slower than training, because at training you can actually do everything at the same time. And this is important because this is one of the motivations why the transformer was proposed. The other implication is not only an implementation one, but it's more about what it's a machine learning one. You have this mismatch in the condition of training and testing. This is not just in translation, of course, it's a general problem of sequence-to-sequence models, the way they are trained. So when you are in training time, all the model learns, think about we are here at training time, it is learning to produce the translation of a word given the correct history, right? It is never learning to generate a word after whatever it has generated based on its own beliefs. So do you see a problem potentially here?
If I understood it correctly, it will be a problem that maybe our model already know how to translate it, but it's translated in the other way, but we force it to do it in the direction of a grant true, right?
Yes. It's maybe you said it in a too positive way. You said the right thing, but it sounds almost... Well, actually, the problem is that the model is never exposed to a history that it's being generated and then or will be most probably flawed. So it never learns to recover its own errors in other ways. Is this clear? So this is also important because all this research around reinforcement learning or minimal risk training, if you will hear about this, is motivated mostly by this fact. So there are ways, but they are quite difficult to come up with and to actually work in practice, to let a model explore, that is, produce a little bit of the translation and then learn also to recover its own mistakes. But it's very difficult to do in practice. Okay, so for the rest of what we are going to see today, we are just talking about maximum likelihood estimation, which is this framework that I presented. You just use whatever you have in the parallel data as your gold sequence, and you learn from that. So, okay, there's this first enhancement that you can do to improve the encoder part. So when the first NMT models were trained this way, people noticed that if you have a slightly long sentence here, you would basically start forgetting what was encoded at the beginning of the sentence. So this was not a very good representation of the whole sentence. So, and also maybe in some languages, well, I will not go into that. It will just confuse you. So anyway, just to say that this part of this sentence could be forgotten at some point. So one rather easy thing that you can do is to do right to left reading instead of left to right reading or encoding. So you can just swap the arrows here. Why not? I mean, we read from left to right, but why should a computer read from left to right in principle? I'd like to think that there is a reason for, but actually you could even have both, right? So I know that Barbara talked about this, but I want to put it here again and highlight one important fact. It's not that these guys are bidirectional. So the states are not bidirectional per se. What you're doing here is very simple. You do, first you do left to right reading and encoding. Let's say you do it first. Then you take your sentence here, you reverse it, and you apply the same thing. So these two things are done independently. So instead of having your sentence representation here, you will have it here, after reading everything from right to left. And this different representation will remember more about the stuff that is on the left of the sentence. And then you can put them together, but you are actually just putting them side by side. You are concatenating them. So this is not a more clever encoder, really. It's just that you have reading the sentence twice in two different directions with exactly the same encoder. Well, with different parameters, but the same architecture. So what you're going to do, you concatenate them and you put them here, and then you proceed. Is this clear? So I think it's, for me, it's quite, it took me a while when this was proposed to understand, because I was thinking, oh, nice, now this representation of movement depends on the freedom of, but also on the verb that follows, so it's a better representation, but it's not. Actually, you have one representation for everything that's to the left, and then you have one that from everything that's to the right, and then you condition your target language model on both of them. But yeah, that's essentially, they're still the same thing.
You mentioned that training is fast, but inference is slow. But on a recurrent model, wouldn't it be the same? Like, you need to wait for the hidden state anyway in training too. You mentioned that training.
Yeah, no,
is
you're
fast and
right.
inference is slow, but
There's some parts that can be parallelized, but not all. This part can be parallelized. Whereas when you are generating the sentence, that's not even parallelizable, because you don't know what the word will be. And this could be a rather costly operation, actually. Yeah, okay, so attention. So I think it's good to see the same thing explained twice. Should improve your understanding of it. So we have mentioned the vanilla encoder. I'm not going into the difference between vanilla RNN and LSTM and GRU, because Barbara covered that very well. So most of the time, these type of neural MT approaches are done with LSTM or GRUs, because they are simpler, but they also work really well. But I'm not zooming to that level of detail now. So we talked about the problem of fitting the whole sentence into one vector. The first solution is to also read from right to left, but fundamentally the problem is still there. So what does attention do? So actually I will use the same slides of Barbara. So you're already familiar with these slides for a recap. So the core idea of attention is when decoding, you basically perform a linear combination of the encoded input vectors weighted by attention weights. So you have a mechanism to look at the whole set of encoded vectors for your input. And you have a function to weight some of them higher than others. So let's talk about translation, because today we're talking about translation, and going back here, and maybe we could think that, so we are going to translate this word now. We have translated è necessario, which means it is necessary to, and now we have to translate what's after this. So I think you could also guess that some of these vectors should be more relevant than others to translate at this point. For instance, which vector would you like to pay more attention to? Very simple exercise here. Well, think about it in the context of translation. So where do you think the most important information is going to be at the time of translating the word after it is necessary to? It's not that easy actually, because this particular sentence pair is not, it doesn't have a easy word-to-word translation. So actually well, maybe if I show the input, that's even better. So we have translated somehow the translation of this part. So what should be encouraged? The subject of this, which is this word. So hopefully we would like our model to pay more of its attention to this vector when it's time to translate this word. But we wanted to find that out as part of the training, right? We don't give any word alignment when we train neural machine translation system. It just sees whole pairs of whole sentences, doesn't have any word alignment. So it turns out it can actually learn to do this pretty well by using this mechanism. What it will do, it will basically compare, if I go back here, it will have a way, clever way maybe, to compare the state vector where we are now at time t with all these other vectors. And it will choose the one that is most compatible to the one that we have now. It will assign a higher score to that. And then it will make a weighted sum of these vectors. But because it's weighted, most of the information will come from the vectors that receive the highest weight. Why this works, I must say, remains still black magic to me. I mean, mathematically, okay, but it's pretty awesome that it works. And so how this is done more in practice, we have a query and key pair. We call it that way, but essentially our query could be this guy, and our keys are all of them. So we are comparing this query to this key, this query to this key, etc., etc. And we get scores of their similarity or compatibility. Then we use a softmax function to ensure that it leads to one probability distribution. And then we use this to make a weighted sum of those same vectors. It looks very circular in a way, because you look down to understand what should be the score of each vector, and then you use these same scores to make the weighted sum of those vectors. And this produces the context vector. And the context vector, how this is used, basically you can think that it's going to replace this older style context vector, which was static because it was the result of this encoding, and it was 1, or in this case it was the concatenation of 2, but it was static. It would just paste it there and then the thing moves on. But what you're doing now, instead of doing this and then generating, you can compute a new context vector at each time step that is also dependent on the target sentence that you have observed so far. So it also takes into account this particular way in which this sentence has been translated so far. So for instance, this sentence did not choose a word-by-word literal translation to translate this sentence. So this should be taken into account when we decide where to look at. Is this clear? Yeah, please.
Do we completely replace the sentence representation? We could also just concat the sentence.
Yeah, it's a very good point. So in fact, what you have usually, you have a way you take this, you could have some simple transformation of it, and you use it to just get started there, because you have to initialize somehow this hidden state at the beginning. But then you will also feed, I think it's in one of the equations, I haven't presented yet. You will also feed this context vector that is dynamically computed at each time step. Yeah, it's a very good clarification, yeah. It's here. Yeah.
I have a question, because as I understand the intuition between, why we use the gate units like in the LSTM in the GRU, this is because we forget the words from the past. So if it doesn't work, we use attention because it doesn't work. The gate units doesn't work that well to give us the information from the past of the sentence.
Mm-hmm. So you are, no, wait. So I'm just trying to reformulate your question. So you're asking whether attention is needed because the gating system in the recurrent unit doesn't work so well.
Yeah, exactly.
Well, I think partly yes, but that's not the only reason, because, well, I can make some parallelism, hand-wave parallelism to how people translate. So you could think of the sec-to-sec without attention as a translator that has to read the sentence once, then he closes, it doesn't look at it anymore, and it has to make the translation. But why? I mean, this is not what happens. At some point, you might want to look back and look at a specific word and pay more attention to that and decide how to translate it. And there is this also, there is this fundamental limit on the capacity of information that you can store in one vector. So the longer sentence will be less well represented. And attention, that's really the crucial thing. Attention doesn't care so much about the length of the sequence, because it's doing its comparison for each of the query key pairs. So, yeah. Yeah.
This is a question maybe more about attention. I haven't worked with it, so I'm not sure if it makes sense. But why wouldn't you want to have, for example, two attention mechanisms? One to maybe keep track of semantic relevant words, and one maybe to track syntactic information. Would they just collapse?
That's a very good question. So you could be inventing the transformer if it wasn't invented yet. So you would like a way to have different distribution, not only one, but say n distributions at each time step. That's exactly what multi-head attention does. We'll talk about it after the break.
Can I ask one more question?
Yeah.
I'm always a bit confused that we also condition the decoder directly on the previously generated word rather than just the previous state of the decoder. Is this sort of admitting that the decoder state doesn't really record that well the previous generated word? So shouldn't it be able to just remember, I mean, the decoder state, the previous decoder state, shouldn't it be able to remember the previously generated word?
So you are talking about the decoder that doesn't have this input here.
Yeah. And on the other extreme...
Yeah, I see. Well, yeah, I guess you
also, if we need this to directly condition on the previously generated word, then why don't we also perhaps directly condition on two words before, right? Why just one?
Yeah, but that's happening when you use the recurrent unit in a way. So 1 second. So this will depend on this specific word here, and this in turn will depend on this state which depend on that word. So it depends on everything before. You are saying, I'm thinking whether, I'm sure in practice it doesn't work very well because there are different ways to input this. And this is the most expensive that you have, the one where you have to wait to generate the word and feed it. And this works the best. So, yeah, why, in theory, why you need that?
Do you want to add something?
Well, I guess there are many ways to actually generate a sentence coming from that word distribution. I guess you would want to know which one you actually chose for your particular sequence that you're generating to inform the rest of the hidden states.
Oh, right, because you may be sampling, right? So the previous state actually sort of encodes the entire distribution of,
yes,
of
exactly.
the vocabulary,
and
but you don't really know which sample you got actually.
That's
right?
to really simplify. Maybe this had two very high peak word choices that led to very different decoding paths. Two alternative way of producing a sentence. You would like to actually condition on the one that you are following, not
right.
another.
Do you want to add something to this?
There's no way you're sampling there, because then you wouldn't be able to get a gradient on it. You can't back propagate on sampling because it's non-linear, and you can't back propagate on sampling, so you wouldn't do that. And also that's a way to actually insert the target sequence. So you could use that.
That's what I said.
Insert the target sequence.
I think you could do it without.
You're right that you can't backpropagate through the sampling, but you are actually sampling. It's just, that's what you do there. I guess anyway, we should probably talk about that offline because we're wasting your time, I think.
Yeah, but definitely the recurrent unit, by its formulation, needs the previous hidden state and the new input to make a step.
The previous word is the embedding of the previously selected word.
Yes.
Right? So you have sampled there.
Sorry, you have?
You have sampled from the
test
distribution.
time, yes. At training.
Also,
no,
at training time you use the gold previous word, right?
Yeah.
You do teacher forcing. Right, okay. Sure, okay, yeah, you're right. Okay.
Yeah, so to wrap up on attention, this was my way to draw it for this particular case. So this word had more importance. So when you do the sum, the resulting context vector, will mostly look like this. And what you would actually hope for in the case of translation is that you mostly have very peak distribution after the softmax, where you're mostly looking at one time step or two maybe, and the others are blanked out. That's what happens most of the time. This is for machine translation. If you're doing image captioning, maybe you want to pay attention to a larger region of the image space. It's really task specific, but for attention, that's what you would like to look. And in fact, I think I have one attention visualization that, it's the same that Barbara showed because it's from the Badanao paper. So the nice thing, when attention appeared, it was the first way we could actually do some opening the black box thing. It's very easy to interpret this. Well, it's very easy to visualize that. Interpret, it's actually another thing. So if you look at a sentence like this and its translation, what this is showing us is, let's say that the input was the French sentence, the output or the target was this one, the English one. So this is telling us, if you look at a column here, it's telling you that when the model had to generate it almost only look at the word L, the first one in French. And then when it moved on to generate agreement, so before generating agreement, This is quite crucial. Before generating agreement, it looked at a car, the previous one, with the even higher score. So this distribution was more peaked. There is a little bit of attention here for some reason. And then you can continue. And it starts really looking very nicely like a word alignment matrix that we used to have in the days of SMT. But it's continuous. That's nice. So you don't have to choose only one word. So in some cases, you actually want to look at more than one word because you don't have always a one-on-one correspondence. So this is the case here. For instance, when we had to translate, the model had to translate was, put most of its attention on a et. This is a very, I guess, nicely cherry-picked example because it looks almost too nice. So was, when it had to translate was, it looked at a et, which is a very accurate way to align these two sentences. And there's also something else to say about this, that actually the model is not paying attention at one word at each time. It's paying attention to the hidden vector representation, which is itself the result of a recurrent operation. So these vectors, they already encode in some of the context. So in reality, you don't even need to expect to see something like this, because the model might have a different strategy to pay attention to what was actually in the input of the sentence. But in practice, most of the attention matrices can look quite nice like this, like what one would reasonably expect them to do. This is also made the word reordering model obsolete because the models suddenly started to know very well how to reorder. Well, is it actually reordering anything even? We don't know. Maybe it really has a very deep way to represent the meaning of the input, and then it uses its knowledge of the target sentence to generate the sentence with the subject at the right place, the object at the right place, the verb place. Because we don't model direct correspondences of the phrases in the source language to the phrases in the target language, we don't actually need to say much about reordering. But we don't know what the model is actually doing inside. Questions? Yeah?
I don't remember that exactly, but is it the case that depending on the different type of attention, the different type of way that you compute the attention scores, for example, like Bardano is doing the MLP that has some parameters, whereas like if you do the dot product or whatever, which is simpler. So is there any kind of like connection as to whether you learn, one of them learns better to reorder than another one, or the model will learn to do that anyway?
Don't know, because the most important paper that compared these different scoring function, it was only evaluated on final translation quality. But I would guess someone might have done that study, because there at the beginning of NMT there was quite some interest in trying the model it's actually trying these alignment matrices to look as much as possible at the word alignment matrices, because we thought that we could help the model by, for instance, you could actually use a word alignment and use it as an additional training signal and encourage it to pay attention to the word, mostly to the word that are actually aligned to the current word. But I think that was quite quickly abandoned, because it mostly helped in getting maybe the model to converge faster. It could be like at the beginning it doesn't know where to look at, so this thing would look like very much uniform and random, and you could give it as training, you could give it a clue early on where it should look at. But if you just wait till the end of the training and you have enough data, that doesn't really matter. it will find it the best strategy itself. I am not aware of whether different scoring function results in a line like attention matrices that look more like word alignment matrices. It could be, but I'm not sure.
Okay, thank you.
Yeah? Okay, so to put it all together, if you take an architecture very much similar to this one, bidirectional encoder, attention, and you you add a few more layers, you stack a few more layers. That's something I'm not showing here because it take a long time to draw, but actually you can put another layer of these guys here, even more. And definitely you need more than one layer of RNNs to do good at translation, if you can afford it. And similar to here, you can have another layer of recurrency stack upon that. So such a model with some decoding tricks and other things that maybe are not shown here was the first neural MT model that replaced phrase-based SMT in Google Translate. And phrase-based SMT was behind Google Translate for a long time. Yeah. Yeah, we have a question, please. Oh, you need the mic.
How does the matrix of attention weights look like? I mean, you have one weight for every time step, one column of weights for every time step, in which each row is every
you mean this
state.
one? No.
It's not the matrix of weights of the attention.
The distribution.
No, I don't think it's represented. It's how. Yes, exactly. Yes, the ST, exactly.
It's different, and this is actually exactly this. Is this? You see? It's important. It's good that you're asking this. So here we are looking at in a very zoomed in way. This is for one time step. No, this one. So we are at time t.
Okay.
And we are paying attention. This is fixed. We have 4 input words here. And this is the resulting of attention at time t.
Okay.
When we do it at time t plus 1, it will look completely different. Okay? And you can also visualize it in a more compact way, like this.
In the slide of Barbara, Mr. Barbara?
The slide of Barbara shows only one time step.
Okay.
Only one row column, sorry.
And the one red circle multiplies every element of the green vector?
Sorry.
One red circle multiplies every element of one green vector of each one?
It's a sum. It's a weighted sum. Maybe you can see it better here. I'm not sure. Is this clear or not?
Yes, all the elements of one hidden state are multiplied by the same number.
So you mean we don't do an attention for each of the dimensions? Is that what you're asking? No? I'm not sure. We don't. No?
I mean, a recurrent hidden state is a vector, right? Every
yes.
element of that vector
in this case, it's a 4-dimensional vector, yeah.
And each of these 4 elements is multiplied by the same attention number.
When you do the weighted sum, right?
Yes.
Yes,
there is one number for every.
No. We don't do it for each dimension. We do it just like you see it here. So the first guy got a lot of attention, so it's darker, the whole thing. The second one didn't get almost any attention, so the whole thing is multiplied by a low weight. Maybe, and the equation is yes. Of course, notation can be very confusing. These are vectors, right? So you have one weight for one vector, one hidden state, which is n-dimensional. And that's why you can also see it like this. Is it clear? Yeah. Okay. Any other question? Yes.
Thanks. I would like to ask about, you said about something about the system being able to recognize its own errors, being difficult. And then there's now obviously the bonus of the neural translation over the grammatical one is that it's more robust. Like the grammatical one could translate everything.
The grammatical
is correct. But, pardon?
Can you, I didn't get your
If you
last
use a completely grammatical approach to translate.
You mean like a rule-based?
Like a rule-based,
yes.
Yes, then that translates well as long as the input is completely correct.
Mm-hmm.
But the neural can translate things that consider some error, so it's more robust for the input, obviously. It seems like, anyway.
But what do you mean by input? Do you mean the source sentence or the target sentence? Because what I was mentioning, what I was referring to before, with learning to recover its own errors,
yes.
it actually meant that it should be robust to the errors that it makes when translating. So that would be on the target side.
Yes. So I assume that the Google's present-day solution is neural,
yes.
Right? So there is this funny phenomena that you can input, you can type in things that are complete nonsense, mm-hmm. and it recognizes them to be of some language, and then it even gives a translation to that. How to tackle this kind of problem? You can write things like oi, 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 and then it proposes a translation in Hawaiian or whatever, and it's complete nonsense, and then you add a few more ois, and then it gives a different translation for Hawaiian.
Is it really a problem? I mean, why would you expect to say this is a bad sentence instead? I mean,
well, I don't know, but it does it. That's the question: is that how to tackle?
But what is the correct sentence of oi, 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 oi? I mean,
there is none. It's just rubbish.
Exactly. So it's really arbitrary. I can just say something and I can claim that.
But you don't see this as a problem at all.
No, maybe I would see the opposite problem, that if you have a real sentence but with some disfluencies, some errors, then I hope that maybe it will be able to recover it. That would be a nice property, but or I would be worried about the opposite, that I put a logical sentence and it produces oi, 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 which was actually kind of happening at the beginning of Neural MT. Sometimes it would just go the wrong way and you would have a catastrophic translation for a correct input sentence.
Yes.
That is a problem. But it has really improved. If you look at the latest version of Google MT, again, modulo the language pair, I always say some language pairs it doesn't work very well, of course. But yeah, to me the problem is when the output starts going crazy, but the input is correct.
Okay,
but if the input is wrong, I mean, why is that? If the input is nonsense, can you think of a scenario where this is an actual problem in the real world?
Well, like text that has a very low quality because of the spelling mistakes, or the PDF to text transformation gives a really low quality stuff, and then it's basically rubbish, and then you run it through a translator to know what it means, and then it translates something that is nothing into something. Maybe,
but then maybe we should think about building a quality controller for the input quality, for the input set. That's another task. I mean, it's not the task of translation. My opinion, we can think of a task that it's taking a sentence and it's telling you, okay, this is rubbish, I don't want to translate this, and then yeah, why not? If you have data for that, or you want to do it rule-based, why not? Like a sentence acceptor.
Well, the rule-based is of course too strict, so that it doesn't allow.
Yeah, but honestly, I see that as not really as a property. I see it more as a limitation, because there are many scenarios where you would like your system to translate a sentence that is not perfect.
Yes, exactly.
So
okay, thanks. I got it.
Sorry to interrupt. This looks like a good conversation to have over
yes,
coffee.
Yes, you're right.
So we should at some point soon stop for the coffee break, but Arianna, you select the exact point.
Yeah, I think we can stop here and then we continue with Transformer afterwards.
Thank you.
All right. So yeah, I have a few, just 2 more slides about the applications of this architecture. They can be really many. So you can change the modality of the input or the output sequence. You can get a speech recognition system. You can have a speech synthesis system going from text to speech. Video captioning, text summarization works okay. You go from a document, full document, to its a summary. And yeah, crucially, the engine that you can use there is pretty much the same. So it's a very versatile architecture. It works really well in a lot of different applications. But it's not the very best one at the moment. So we are going to talk about another one in the rest of this talk, which is called the transformer. Before that, actually, I had a little digression on trying to compare neural MT against SMT as a paradigm. So what has been solved or extremely improved by neural MT, some of the things have already been mentioned by Barbara. Models naturally capture form of distributional semantics of words and phrases. This is really important. So this goes back to the idea that instead of counting over atomic units that are the phrases in phrase-based SMT, for instance, you have this continuous representation that allows you to capture and share information about similar words. And this is important for many reasons. One of them is that you make much better use of the data. And the other one is that you have a much better overall grammaticality of the output sentence. This is just an empirical fact. There is a clear reason why that is the case. It's because we don't need to do Markov assumptions of any kind anymore. With the recurrent neural network, we can actually model dependencies that are of arbitrary length. Of course, it doesn't work perfectly all the time, but before we were clearly missing a lot of dependencies in the sentence. So I'm not sure that I have a good example here, but the typical example in English is a subject and verb, for instance. You can have the key that I lost yesterday when I was going to the beach has now been found. So there is a dependency there between the key and the verb has. And to get the verb form right and its number, you need to remember what the number of the subject was. So this is just a grammatical example. I think Barbara had more topical examples, so dependencies at the word choice level. And also, as I said, word reordering is basically solved with neural MT, which is impressive, at least in the languages that I know of, and I had been working with in my PhD with SMT methods. But yeah, so I leave it to here now. At the end of the talk, hopefully if you have some time, we'll talk about things that aren't working so well. But while you're still, okay, actually now I have one anecdotal slide of what happened back in 2014 when this neural MT was still really new thing, and I decided to just try this online demo that they had for English to German. And English German was one of the languages with I struggled the most when I was working with word reordering. So I had a lot of interesting examples there. So yeah, here is an example of also long dependency and reordering in translation. So perhaps when you translate into German, you have to move part of the verb at the end of the sentence, but one remains where it is in English. So this is the translation that I got from this online demo. So it was before all the twists and bells of NMT were proposed. It was still version 1.0, and yet it did a very good job of reordering the verb. Yeah, this was very difficult in phrase-based, very, very difficult. So that was my reaction, and that's when I realized that, okay, now it's time for NMT, time to move on. So now let's move to more hardcore stuff, transformer. What is transformer? I like to call it a fully attentional network because it's what it is. But it goes more with the cute name of transformer nowadays. So what's the core idea behind this model? Which, if I am not mistaken, is actually what's behind Google Translate at the moment, at least in many language pairs. The core idea is just the title of the paper. It's that attention is all you need. So in the architecture we talked about so far, we had these two important concepts, recurrency and attention, and we put them together. Now we would like a way to get rid of the recurrency. How is this actually going to work? So we can start from the observation that attention has a major impact on sequence-to-sequence performance, and that recurrency is an obstacle to parallelization. So if you are a big firm working with huge amount of data, it's actually an important thing for you. You would like this to be much faster. You would like to get rid of the recurrency. So the question is, can we build a fully attentional sequence-to-sequence without recurrency? And that seemed pretty impossible, not impossible, but to me counterintuitive, because recurrency is precisely what gave us all this modeling power. It gave us this sentence level representation that encodes the full sequence. And it has also a rather nice interpretation. It has a cognitive motivation. Why do you want to get rid of it? And how can you do that? So this is, in a very, very simplified way, what we are trying to do when we move from RNN sec to transformer. So for now, we ignore the different colors of the arrows. Just look at the way the information flows. So what we have here, these are the input each time step, and then we have two layers of, on the left, recurrent units, and on the right, transformer units. So on the left, we know that everything at each time step and each layer has to be fixed has to be squeezed into a fixed size vector. That's our state. And that's how the information flows. It always only flows from the previous hidden state, h of t minus 1, this guy. And it flows from the current input to the current state, x of t goes to h of t. Whereas on the right, what we have there, we actually allow the model to look at everything, to the whole sequence without any limitation. And we don't have any link between states, hidden states. Okay. So these are really the two different paradigms. Now the orange arrows, what it tells us, if I remember when we drew this graph, it's showing how information from a given input, for instance the orange one, can flow to the current state, which is the purple one. So you can see that there is a bit of information that should flow from orange to purple. It has to go through all these paths. It has to go through a number of recurrent connection here. There's all these dependencies, but there is no direct dependence between these two blocks here, okay? But in the transformer, actually, the path is much shorter, because this state directly depends on this one, and then this goes up for there. Or you can go from here to here and all these other ways. So it's not just better computationally wise, but supposedly it has easier access to all the history in the sequence, and that could give it an edge to represent long range dependencies. Yeah, sorry. Is this kind of clear so far? We'll look at it in detail, of course, but this is the general picture. All right, so this is the actual transformer, and you have to multiply that n times on the encoder side, which is represented on the left, n times on the right side, it has a lot of sub-layer operations. There's a lot of strange things. And after all, I think this is a good name, transformer, because it kind of looks like it. It has all these strange gadgets inside, and you don't really know at first how they work all together. I still don't know how they actually work so well all together. But yeah, let's get started. So, transformer architecture overview. A bit of a closer look. So now, as I said, there is no recurrency. So how do our encoder look like? Basically, we are going to do attention between, okay, let's start with the first layer. We're going to do self-attention. So maybe, okay, sorry, let me go back 1 second. What I have here, was an example of, on the left we have left to right reading for recurrency, and on the right we have attention. But actually, one crucial thing is that you cannot only, you can do attention between the target sequence and the input sequence, but you can also do attention on the sequence itself. Does it make any sense? So when you are doing language modeling, there is no source sequence. You're just modeling a sequence in a language. You could also, why not do attention on the history, on the previous tokens that you have observed or generated if you are doing testing? Actually, you can do it, and that's called self-attention. So we are going to see that transformer has 2 types of attention. The first is self-attention, and it's used to replace recurrency in the encoder. And it basically looks like this. You look at the first layer. Well, the very first thing to do, as usual, go from the word to the input word embedding. And then for each of these blocks, we are not going to call them time steps anymore. This is important because there is no recurrency, hence there is not really time dimension here. For each of these words, we are going to do attention, so a very similar operation to the one we described before, to obtain this representation of the word. So what this represents is a first encoded version of machine in the context of its full, of this full sentence. We're going to do the same thing for this other word. So we get a representation of translation in the context of this particular sentence. We do the same for is and for fun. And then we are going to repeat this for a number of layers. Here only 2 for simplicity, but usually more, 6 for instance. And the representation becomes deeper and deeper, whatever that means. But essentially the operation we are doing is the same, but with different sets of parameters. Is this strange, logical, clear? Do you see something missing? Something that could be a problem here? It almost looks too simple, right? No. So one thing that I can already anticipate, we'll talk about this a bit later. If I scramble the order of the sequence, I get exactly the same thing, right? Because it's nice, I drew it like that, but the model, it's just a graph, right? It doesn't know anything about the position and the relative position of these words. It's like a bag of word model. So actually we will see that we need to add something without doing recurrency, but we are going to add a way for the model to have to capture the position of its word. Okay, but let's continue with the architecture overview. So this was the encoder, now we have the decoder. The decoder looks quite similar, except that it makes 2 types of attention. It makes an attention to itself, self-attention, or to its own context. And it also has an encoder-decoder attention. Finally, that's where translation comes into picture. So if we are looking at this particular word, let's say we are at training now for simplicity. We are at training. What's the input to this state here? We have the word that was just before, that had to be produced before in the target, and all the other words that appear to the left of this word, but only to the left, of course. We are not allowed to look at the right of the future, otherwise it would be too easy. And we also have attention to all the output vectors coming from the last layer of the encoder. So translation here, and here we have capturing the context in the target side. Same thing here, we need a way to tell the model that this is the first word, this is the second one. We will see later how this is done. So on some levels it looks similar to what we had before, but it's actually very different because the states don't have hidden-to-hidden connection here. Okay. Is this clear so far? Yeah. Maybe the microphone is arriving.
So, if you go to the slide where you put the diagram of the original...
This one?
Yeah, I understand there that out of every of the n layers that you will have in the encoder, you send information to the decoder, to each of the layers. Is this correct? Because you have this last arrow after add and normalization in the first block, but this means that this is done at every stage of the decoding, like for every layer.
So you are asking if you could have these dotted arrows also coming from here?
Yeah, that's the question. Like not if I could,
Yeah,
but if that is what it's done. Like these dotted arrows.
It has been tried, and I, at the moment, don't remember if it really matters. But it's totally possible to do it. Why not? Because you are doing this. No, okay. When it's self-attention, it's always to the layer n-1.
Yeah.
Attention to n-1, and then so on. Here the same, and encoder, decoder attention, you have the choice what you want to look at. You could look at all of them, you could look at a combination of them.
Yeah, but the traditional implementation, or the one that everybody uses, does it do this, or it's just
so I think in the paper it's like this. If someone knows differently, they can correct me. I think in the paper it's like this, and then in some follow-up papers they tried all sorts of variations. Do you think it's it could be an important?
No. I just think that I have tried to understand it, and it was one of the doubts that I had, like whether this, because of the diagram, it looks like
it's
they
true.
are
The
sending
diagram
it every
is
time.
very high level. It doesn't say much about this.
Okay, I have also a question regarding to make clear the architecture of the encoder and the decoder blocks. So it appears to me as if these are both feed-forward networks, but is the self-attention in this case something like a layer-wise operation or something like that?
Yes. Is it not a layer-wide operation? Is that the question?
No. Is it actually, can the self-attention be considered something like a layer-wise operation in the context of the feed-forward networks that are that consist encoder and decoder?
I guess so. Yes. I'm not against this way of describing it.
Okay.
But attention is different from a feed-forward neural network.
Okay.
In fact, you have both feed-forward and attention here. We are going to zoom in here. This is only one of the first views.
Okay, great. Thank you.
Okay. Just wanted to make sure that you got the general picture. Yeah. Yeah, maybe, well, so just to make sure, this is not the last slide about transformer. Don't worry about it.
Can I ask a question?
Yeah.
Does every layer in the decoder take as an input?
Can you speak up a bit?
Does every layer in the decoder take as an input the last layer of the encoder? Or
yes. If this picture is right, you mean so we are doing attention to this layer at each layer of the decoder, right? So we are doing attention over the same set of vectors at each layer of the decoder. Is that the question?
Yes.
Yes.
Okay.
But I think before someone asked also whether you could actually look at different lower layers of the encoder, and you can, definitely.
Okay.
I just think, if I'm not wrong, this is the formulation that they have in the paper. Okay, so now, yeah. Now, okay, this is for another word that we have here. So you have the same thing basically for another word, except that, maybe this is something that's good to say, for this particular word, we look at we do attention over 2 target symbols, whereas for this one, we pay attention to 3. The current, the previous one, and 2 before. All right. Whereas here, we always pay attention to everything because the input sentence is fully given at any time. All right, so now you know what's the general framework. Let's look inside this thing. So we are going to start with multi-head attention because that's really the core layer that we have. Well, layer, what should I call the core mechanism that makes transformer work. So transformer uses a particular type of attention. It's called the scale dot product. So let's really not get scared by this because it's just one way of doing the scoring of attention, like we had said before. They happen to choose this one because it works well in their architecture. So remember, we needed a scoring function when we are comparing the query vector to all the key vectors to decide how similar or compatible they are. And there is the dot product is a very simple and fast to compute one, and it works pretty well in practice. So the intuition, the rationale is simply that if the 2 vectors are similar, then we'll have a high score, and therefore more attention paid to that particular vector. However, it has been observed, so this is really empirical problem, that if you have very high dimensional vectors, the softmax, so the distribution that you get out of this when you put all the scores together, it gets very peaked and the gradient's very small, so learning doesn't work really well. So the solution is simply to divide this by a fixed quantity, which is the square root of the dimension. I think they tried a bunch of different things and this one really worked really well. So this is just a particular type of doing attention scoring. We're going to take it and use it for the rest of this explanation. Now this is maybe more involved. They introduced a query key value abstraction in their attention. So we have talked about query and key, which in the context of machine translation pre-transformer, the query was the current hidden state at time t when on the target, and k was swiping through all the encoded representation of the input sentence. Okay, now you have to make a little effort here and think that we are doing self-attention. So we are in this context. I just drew this for one particular word, but of course this is happening for each of the words. So each of these vector has to do attention on all the vectors in the layer before. So it's also comparing to the layer n-1 representation of the same word. Okay? So how do we do that? The simplest way to do this is to have query and key come from the same vector. So there is basically no abstraction. You take a vector, this vector here, you compare it to itself, then you compare it to the vector of the word before, then to all the other ones. You have a score for each of the pairs, and then you transform this into a distribution using softmax, and then you do your weighted sum. However, there is a better way to do this. Why? Because maybe there's different aspects of a word in context that you would like to preserve to use as the query or as the key. So how we can do that is by introducing this abstraction of the query and the key and the value. We can learn multiple views of the same vector that we are going to be used for different purposes. Yeah, question.
So neither of query and key are the input? Like the input to this layer is different from the query and the key, right?
So what we are doing here, we are at layer n, let's say, and we are preparing the scores to compute layer n+1. Okay? So that's all we have right now, let's say. We have this layer. We need to prepare the scores, so we will have attention to go to layer n+1. Does it make so? Maybe let's say that we are here. We are still here. This doesn't exist yet, okay? So we are here. We have to derive our scores that will be used to make the weighted sum, and the result of that will be placed here for each of the words. Yeah, maybe a different way to think about this is the first layer will be the word embeddings, right? So it's just the embedding of the translation of the word type translation, the embedding of the word type is and fun. Now we want to have a version of these vectors that is context sensitive. So which word in the context should have more weight in modifying this vector? Is this a bit clearer now?
Yes, I thought this was a definition of self-attention.
Sorry, this was?
I thought that this was self-attention.
Yeah, it is self-attention. Ah, you mean the query and key?
Yes.
Now. Oh, yeah, okay. Yeah, but I'm introducing the terminology of query and key. But now, if you want to do something meaningful with it, you're actually learning different views for each use. So you take the same vector and you project it through different matrices, whether you want to use it as a query or as a key. And we go to the value in a moment. Just talk about the query and the key. Yeah? Can you look at the picture now? Is it... I'm going too slow, perhaps. I should go a bit faster. The drawing will help. All right. Now, I think it's important because also in the way they are using this terminology in the paper. So the query and key, first, it's just a term. The query and key could be the same thing. But we can actually learn different transforms for different purposes. So here it still doesn't say how we go from here to here. Let's just say that we learn multiple views of the same vector. And now we are going to compare this, for if we are looking at translation here, we are going to compare the query view of this guy to the key of all the other guys, including itself, right? Okay? So we do the dot product at each time between this query and the key of all the other words. And we get, again, a distribution. And then here is the value comes into the picture. What are we going to sum at the end of the day? So with this, we use this to do the comparison and the scores, but at the end we have to use the scores to do the weighted sum. So what are we going to sum? Again, we could sum, we could do a weighted sum of these green vectors, or we could again use the abstraction and learn a third view of the same vector, which is going to be used as the value. So I can try to say this a bit in words, my interpretation of what is happening. Okay, let's assume some feature of the words are more important to be used as the query, and some other features are important to be used as the key. So query is eventually referring to the word on which we are doing, that is doing attention, and key is the word towards which we are doing attention. So these two are used, they are tightly connected, we use them to compute the score. But then which feature of the word we are actually want to propagate to the next layer? And this abstraction is given by the value. So we have something very same as what we did before, coming up from the score, and the softmax, we use this to have a weighted sum. And this is the thing in formulas. So I introduced this Q hat, K hat, and V hat that are not in the paper, because I think the paper is, I found it very difficult to follow. But I didn't want to go against their notation, so I added this layer of notation. That is the hat. And what I mean here is basically the transform, the result of projecting the vector to either query, key, or value. Whereas Q, K, and V are the vector itself. And the reason you need this is because there are two types of attention. This is self-attention, but we will also talk about encoder-decoder attention. And when we do encoder-decoder attention, the keys come from somewhere else. So that's why you need this too. So this is just coming from here, but this was written for one value, one scalar, whereas this is written for the whole vector. And you have the same operation here, you have the scaling. So this is the dot product that you use to get the score. You scale it, and then you do softmax, and you do the weighted sum of these the values. Now, where do the values come from? If x is our vector, this one, for instance, the query, the key, and the value, they are the same. They are the vector. But to go to the multiple views, we do this linear transformation using 3 different weight matrices, okay, which are learned. So we have a weight matrix for the query. That's what tells you what features are needed to do the query, which features are needed, I'm really simplifying, of course, to do the query, and which features are to be summed together eventually to be given to the next layer. Yes, we have a question. Yeah.
Are those weight matrices constant through all the layers or per layer?
I think they are per layer. They are different on each layer. Yeah. They will be the same for all the attention operation at one layer, but then when you go to the next layer, yeah, of course they are different. Yeah.
Can you tell us again where does Q, K, and V pop out? Because you do machine, then the word embedding, and then there is Q, K, V. Can you explain again where Q, K, V
So how do you go? So let's say this is X. I should have written it here. This is X. How do you go from X to
QKV.
QKMV with the linear transformation here using three different matrices.
Which are learned.
Which are learned, yeah.
Right. And in the previous picture, self-attention is just a black arrow. No, previous?
This one?
Previous one. Self-attention is only the black arrow or is all of it?
Sorry, you mean this one?
The self-attention is only the black arrow or is all the arrows?
It's everything.
Every arrow?
Okay, no, that's very important. Self-attention doesn't mean to the word itself. It means to the sequence itself.
Okay. Maybe
yeah.
Can you explain again what's the difference between this and a feed-forward network?
Well, this feed-forward network,
like
it has a fixed dimension. You cannot do a feed-forward network on an arbitrary long sequence. So in the feed-forward network, you would fix the size of the input. Let's say, do you want to make it 4? In this case, it would capture the whole sequence. But if now you have a sequence of 5, because you're learning weights, different weights for all the 4 different inputs. And this is really different what we're doing here. Here I can put 100 long sequence, and I can still apply attention. Does it? No? No, that's the thing, because you do it pairwise. You do it pairwise. You see? You do compare, maybe you want to stay here, you want to compare this with this. Compare this with this, this with this, this with this. Get a score, normalize, sum all together.
The question is there an activation function in this, or just a multiplication of the weights and the input?
Yes, basically, because I'm going to see if I have the whole, I have to go back. Weighted sum? So you mean like a nonlinearity? There could be a nonlinearity in the scoring function if you could use a small feed-forward neural network to do the comparison, but the input to that is just 2 elements, the query and the key, because you always do it pairwise, okay? So there could be a nonlinearity in the scoring function, but it doesn't have to be. If you use dot product, you don't have that. So it's even cheaper to compute. Are we all on the same page? No? Takes a long time. Okay. Now, yeah, we are not done yet. So maybe you remember in the first part of the lecture, I mentioned multi-head attention. So what is that? There was a very good point this morning that there are different ways in which words could interact with each other. So, no, let's stay here. So one could be, again, simplifying. It's good to simplify. One could be topical interactions. So words, there are topical, there should be a topical similarity between words in the same sentence. Another one is grammatical dependencies. If the subject is singular, then the verb should also be singular in English. Many other things, coreference effects. So we have a pronoun, it, and it refers to some entity that was mentioned at the beginning or very far away in the sentence. These dependencies should also be captured for semantic or syntactic reasons. So in a nutshell, there are different dimensions, linguistically speaking, also in which words can interact with each other. And if we only do attention once, you have one distribution of weight. So it's very hard to capture that, because maybe on some level, word I minus 2 is very important, but for some other effect, it's not important, and word I plus 3 is much more important. So how can we give the model flexibility to capture this? Well, we do multi-head attention. And what multi-head attention does, it gives to the attention layer multiple representation subspaces. This is also not very difficult, basically. We have a replica of the attention with different weights. They are all, of course, initially initialized, and they will diverge and diverge as training progresses, and they will capture different things. Now, whether they actually capture coreference, topic cohesion, etc., that's a whole other question. But at least the model in principle has the flexibility to do different, to learn different things about the word in each representation space, and consequently to learn different attention distribution in each of these spaces. Is this clear? This is also key to transformer. Yeah.
One of the questions I have when we're talking about representing all the different phenomena with the heads, is that something that we typically, in most of the literature, they allow the multi-heads to actually try to naturally learn and figure these out? Or when you're training, do you train one head per task, or do you jointly train on multiple tasks?
You don't give any supervision to this
Okay.
multi-head. Well, there might be work that did so, because it could be really tempting to use this to input some syntax annotation. Maybe someone has done that, I'm not sure.
Okay.
But transformer by itself, it doesn't do anything.
Typically, it's just trying to learn some representations, and we assume that more than one exists, right?
Yes, exactly, and they will diverge. But in practice, we really don't, there is not even a reason to expect that one head will focus on syntax and the other on semantics and the other on some, no, well, it will just try to fit the information in the best way it can. And in fact, interpreting this thing is quite difficult. Yeah, one more question.
So you compute the scores between every word and every other word, including itself. What do you do with these scores then?
With what, sorry?
With the scores, what do you do with the scores?
With the scores, just like before, I normalize them with the softmax.
Okay.
So imagine that these are the unnormalized scores, so this is really high and the other are all low, but they have to sum up to 1. Okay, so you normalize them with the softmax, and then you use them to do weighted sum. Are you saying specifically in multi-head or also?
No, also in the
also
other one.
Before,
because
so
okay.
Yeah.
So Q, K, and V has nothing to do with the scores. It's only the weight matrix. It's a result of the of the matrix product.
First, you use this formula and 3 different learned weight matrices to get Q, K, and V for each vector. Okay?
Okay.
Then you use Q and K to do the comparison pairwise. So if we are now looking at 2, you use query 2 and key 1, key 2, key 3, and key 4.
Okay.
Okay. Each time pairwise.
Okay.
You get a score normalized, and then you use this distribution to do the weighted sum of the values, again, of the same guy.
Okay.
Okay? You want to know next what happens?
Okay.
Okay.
And then
next, this will be used to create the vector of the layer above. But we still need some other computations, but eventually it will result in this.
Okay.
Okay.
So we are not in the next.
We are basically explaining what happens here. This is a very simplified view. Okay.
The arrow. You're explaining the arrow.
This is showing like how the information flows, but it doesn't show you how this is actually done. Okay. And now we are looking at how this is done in practice. That I will also explain that, maybe it will be more clear. So we have talked about multi-head, basically n clones of this querying key and vector matrices with differently, with the randomly initialized ways, and then they will diverge during training, and they will capture different things.
Could I ask, the initial transformation to generate the first K, V, and Q, that's the same for every head?
Same in the sense that it has the same structure, but the weights are different.
Okay. Even
right?
at the
You mean
initialization step?
at initialization, it's all randomly initialized.
Okay.
But all different
But then
randomly.
you said that you use these matrices, right, to transform them, different matrices to transform. Those matrices are the same for the two heads?
No.
Okay.
No.
Okay.
They're really different. So you will have, where is the, yeah, here is the formula. Okay, give me a second, because maybe with the formula it becomes clearer. So we have two different, I didn't draw two sets of this curved arrow, but they should be there. So we do it for this head 1, we do it for head 2. Therefore, we had two different distribution, two different weighted sum of two different sets of values. Everything is duplicated. Then we concatenate these two, the result of these two. We do a linear transformation to have, again, projected in the desired dimension. And this finally is the output of multi-headed attention for this particular input. And there is the formula. So this maybe now becomes clear that you don't just have a WQ.
Okay. Yeah, so you have the sub-I's, the
there
sub-I's
is
are the different one. Okay, thanks.
Can I just go back to one of the previous questions, just to point out there has been at least some work where people have tried to force a particular head or particular heads to look at particular information. For example, there's an EMNLP 2018 paper by Struble et al. On semantic role labeling, where I think they tried to force at least one particular head to look at syntax, for example. But yes, this is not what people normally do. So normally you just let the heads.
It makes a lot of sense.
Yeah.
And I'm curious, what was the result?
I think they show that it does help. Right?
Yes. Yeah. Okay. Yeah. So you could also see it as a new way to, new opportunity to add some kind of supervision that makes sense in the context of your task. Yeah. There is a question here.
Can you turn to slide 56?
56.
No, the other 55. Another one. Oh, no, okay, this one. It looks like the last row, comparing the last row with the row previously. It looks like Q and X are the same, K and X are the same, V and X are the same. Comparing the last row with the previous to last row.
This one? Yes. And
is it so? It looks like X and Q are the same, X and K are the same, X and V are the same.
Yes. So basically, Q, K, and V are a placeholder. But you decide what to plug in there. So because we are doing self-attention, you will plug in X to get the query, the key, and the value. If you're doing source to target attention, we will plug something else. I have the other formula. Maybe when you see the two, it makes more sense, because here you would like, okay, why use all these different letters for the same thing? That's the best way that I could come up to explain what's in the paper, because they also, if you read the paper, they just talking about query, key, and value. But what they mean is basically what you use to, they use it like the term, and what you plug in there depends on where you are in the architecture. So query and key are the things that you use to do the comparison and get the score, and value is the thing that you use to do the weighted sum according to those scores. Yes, exactly. But only in the case of self-attention. You will see that there is another case. Yeah, so we covered this. But it's also the concept that's also behind here, and it's the most important one. So I think we are on time. All right, there is a little more, well, not little, there's one more ingredient, or actually two. that we need to get the actual output of this computation. There is a residual connection that Barbara mentioned 2 days ago. I don't have time to go too much into this, but basically this was a solution to the problem of vanishing gradients, because you're doing a lot of multiplications per layer, and this is a way to make sure that actually the input itself, before we do in this case attention, is also available to this layer. I don't know if I'm explaining this right, but I want to go a bit quicker through this, because I don't think it's a core concept that you need to understand the transformer, but in practice it's really important, and also layer normalization is very important, but that's just to say what's in here. Okay, so this is perhaps more interesting because there were many questions related to this. So in the encoder we only have self-attention, meaning the sentence is looking at itself, let's say, to encode it itself. But when we move to the decoder, we want to do two things. We want to capture both attention to the source, so the actual translation, but we also want to have representation that are context dependent, when I mean target context dependent. So these two things directly correspond to, wait a second, this, okay, self-attention. So encoder it only has self-attention on the source. Decoder has self-attention on the target, but it also has attention on the source. Obviously, otherwise you wouldn't be getting any translation. So this is very important. That's where translation happens. Yeah, so let's see how these two differ. Two types of attention. The first is masked multi-head attention, masked self-attention, actually. What is masked? It's nothing really fancy. It's just that we can only look at the left part of the sequence, obviously. So imagine you are during training, you have the full input sentence, but you also have the full output sentence. But you don't want the model to learn how a word depends on its right side context, because when you translate, it doesn't exist yet. You only have the left context. I see a lot of perplexed faces. How could I re-elaborate that? Nobody has a question to help me? No? Yeah, please.
Maybe it's that previously you mentioned that now we're not doing things from left to right, because that was before with the Arianna. Now we're doing things in parallel.
Yeah.
So now it's a bit of a surprise for us.
Yeah, maybe that's also good, that because attention always looks at the whole sequence. So, of course, that makes sense to do when we are encoding the input sentence, because we want to translate the sentence as a whole, so we can look at it. But when it will be test time, we are going to generate, again, our sentence from left to right. So the model should be prepared for this task, and it should be trained only on the previous words, not on the future ones. I mean, it's maybe an obvious thing, but the way when you actually implement this, you need to slightly change, because our self-attention in the encoder was allowed to look at the full sequence. Okay, maybe it's a detail, it's not so important. But that's why it's called mask anyway. It's basically when you implement it, when you implement training, you have to make sure that the model is not making attention to the right part of the target sequence. And it captures target side context, crucially. This is one. And two, encoder-decoder attention, so this is actually a bit different. It captures source-target translation equivalencies. And finally, that's where we have the major difference from before. The query comes from the target, but the key and the value now come from the source, the encoder. And mathematically, this is how we could write it. So we have seen this before. Take the same X and project it with 3 different matrices, whereas now we have the X for the query projected to the Q matrix. Of course, I should have, I mean, these are not the same matrices. I should have also put another index here because these are different weights, of course. So there will be a set of weight matrices for the self-attention and a different set of matrices for the encoder-decoder attention. There will be also different set of matrices for the target mask self-attention. They all look exactly the same, but the numbers, the parameters inside are different. If you understand this, you have understood transformer.
Why do we have a query and a value and not only a key? Sorry, I mean, why do we have key and value, but not only key? Why do we need both of them?
Why do we need both key and value?
Yes, because
it's a choice. It's also an additional flexibility and modeling power that you give to the network. But you are right. You could also just have, in fact, a number of other models before the transformer had only key, query and key abstractions, but they also introduced a value, because empirically it helps to have a third transformation for the features that you actually want to have in your weighted sum and give to the following layer. That doesn't need to be the same information that you need to do the comparison.
Because if I understand it correctly, then the Arianna encoder-decoder architecture, we had also attention, and in my understanding, we had only key and query.
Yes,
there, but
we could have had value too.
Yeah, okay.
We could, so a lot of things that I'm talking here about the transformer can also be applied to the previous architecture. Absolutely, and it will help. And in fact, this first paper of transformer showed a huge improvement over the previous architecture, but then there were follow-up papers where they do a lot of ablation tests, and they see, okay, if we do multi-head in RNN, in LSTM sec to sec, do we get to the same performance? If we do query key and value on RNN, do we get the same performance? So actually, the difference between RNN-based transformer was smaller than what the first paper could lead to think of, but it still actually works better, even if you control for all this, if you use the same tricks in the previous architectures. But you are very right. Like many of these things can be applied in different architectures. Yeah? Everybody confident they understood this? I hope so. Okay, one more question.
Are you going to zoom in these layers just as you did for the encoder, or are we to ask all our questions now?
Let me see. No, that was the best. So, you mean like if I have something similar for the encoder-decoder attention? No. I was a bit lazy, maybe. No, but I mean, because it's really the same set of computations. But yeah, it has a very different thing. So you could do that as an exercise, maybe. If you have a question, it's better to ask now. Yeah, about this.
So, as I suppose that as you mentioned, we have self-attention and XY attention, let's say. What?
Encoder, decoder, yeah, source target, let's call it. Source
target attention. And in the decoder phase, do we have layers dedicated specifically to the one kind of attention and layers dedicated to the other kind of attention, or is there a layer that we do both? I don't know if I'm explaining it well.
Maybe this will be best shown here, right?
Yes.
So at each layer you do attention on the target sequence itself, and you do it to the source, and they are done. No, wait, here. Okay, so this is the self-attention for the decoder. Add the norm. So actually you do this first. Then you do attention to both.
Oh, so the first part is only self-attention.
The first part, yeah, apparently.
Okay.
Finding out that, yeah.
And the second part also does self-attention. Or no, the second,
That's also, well, yes, because you have this arrow here. Okay, I see what you mean.
Is there more self-attention in the box number 2?
I don't think so. From the way it's written there, well,
it could be. Maybe it doesn't matter so much.
It seems so from this picture. Now you are really asking me a very nitty-gritty detail. Yes. Yeah. So yeah, I would say yes. Sorry, can you say it again? Yeah, but yeah, it's true that there is also an arrow here. Oh yeah, you're right. Sorry. Of course. Of course. I'm a bit tired. Yeah. It's very true, and that's also that explains why so these 3 arrows. There is a lot in this graph actually. So here it's showing the fact that query, key, and value come from the same guy, whereas here, very good. So this will be our query, and key and value actually coming from somewhere else, from the encoder. Okay? Thanks. Yeah. Okay, there is one more thing we need to talk about for the transformer, but I already gave you an answer to this before. Wow, what is missing here? The part that is blanked out? Position, yeah. So without the positional encoding, we still have a bag of word model, largely. It wouldn't work really well. I don't even know if they try to do this without positional embeddings. So the key thing to understand here is that when we had recurrency, that was naturally representing the order of words in a sentence. Why? Because if you unroll the computation, you would have input of W3 coming after W2, coming after W1. Hidden state 3 would depend on W3, but also on hidden state 2, which depended on W2, and so on and so forth. So by unrolling the computation, you have a natural representation of time there. However, this does not exist in transformer, and we need an explicit way to represent a word position. So think of it like we are attaching a flag to each word, saying machine is word 1, translation is word 2, is word 3 and 4. Yeah, really that's what we have to do. And then the model has to do something with this information. So it turns out this particular function is a good choice to represent the position of the word. It's super complicated. It looks like this, and what you have here is these are 512 dimensions, and these are, I think, 20 positions. So this will always be the case, right? The embedding of position 1, I think it's this one. It will always look like this. These are the 512 dimensions. The embedding of position 2 always look like this. This is not learn, okay? It's a clever way to embed a number, really. You take this and you sum it to your word embedding, and then the model has to learn what to do with it, really. One second. The particular choice of this function, I won't go into the mathematical details also because I don't really know much more about it, but the reason why they chose this is quite telling. It's because for any fixed offset of k, so let's say we have the embedding of k equal to 1, the first, there is a way to represent as a linear function the offset, let me rephrase it. So for any fixed offset k, the positional embedded of pos plus k can be represented as a linear function of p, positional embedding of pos. So I guess the intuition here is that it's important, more important than knowing if a word is at position 3. It's important for the model to have some way to grasp that 2 words are 3 words apart or 4 words apart, and that 1 comes before, so it's +3 or -3. And by choosing this particular function, any offset k can be represented as a linear function of the positional embedding. So even if you don't understand how this works in practice, because I honestly don't, for me this is enough explanation. So the model wants to know, for instance, that when it's paying attention to the pair of words, let's take, let's take the words machine and is, okay? Without positional embedding, there's just 2 words occurring in the sentence. But I guess the model would really like to know that machine occurred before is and at some distance from it, and then it could be a really good cue that this word could be the subject of is. I am very simplifying here, of course, but that's to give you the intuition. Okay? Whereas if machine had appear after is, then we should give a different attention. We should use that information differently because it's much less likely to be the subject of that verb, for instance. Who is completely lost? Nobody. Wow. I don't believe. Okay. But we have a question, luckily. No? You mean here? It's the dimension. So it's... It's... sorry?
No, I.
Yeah. So let's see. So we want to have the positional embedding of position 3. Okay, and this tells you the value that will be at index I of that embedding. Is it correct? Yannis?
Is it dimension or position?
So the positional embedding of position 3, for instance, can be described as follows, okay? At dimension 1, I, we will have, well, actually, I don't even know. Yeah, basically, I is going to swipe over all the dimensions of that embedding. It's actually telling you exactly what you have to put in each of the cells, in each of the dimension of the embedding. Does it make sorry? Yes. Well, It's written in the, you could also write it like PE of pos is equal to, and then 4i in 0 to n, and you have a little program that is telling you what to enter at each I. I is the dimension. I think, yeah, this is not the best way to write this. So think of it, it's describing the positional the vector that corresponds to position 3, and it's fixed throughout all your training. No, it's just a vector that represents a number, 3 or 5 or 7. And it's the flag that you will attach to the input word. So when we are here, this is still, it's just machine, but we want to tell it it's machine at position 1. So we are going to sum the embedding with machine to this fixed embedding that is given by that formula corresponding to the number 1. So the representation of the number 1. You sum it to machine, and then you continue. Yeah.
Last time that I printed out those values, it was kind of recurring. I think you could have the same embedding in different positions.
It starts looking like yeah. What? On some dimensions.
On some dimensions, yes.
Yeah, on some.
Bigger ones. So it was like a signature, basically. Yeah.
Yeah, because I think this is, you don't see it here because it's a too short. There are only 20 positions, right? So that's if you go more, you will see a pattern appearing.
If I remember correctly, before Transformer, the implementation of Facebook that was also using CNNs, they just used as a positional embedding randomly initialized vectors that were unique per position. And that worked as well.
Even in the some of the Transformer papers also use that. So
there are different ways to do that, yes. And there is also one I saw recently which learns the relative positioning. So I think this is also trying to capture that.
In ExcelNet, they try to capture the positional, the relative distance.
So you can plug different things in there, but this is the one in the original paper.
I still have a question.
There's another one there.
Okay, whatever.
Okay, sorry. I was just wondering, so we can see in the outline of the transformer model that there's like a feed-forward layer in the last part of the encoder and also at the last part of the decoder. Could you say something about why do we need another feed-forward layer as well?
Yes, that's a very good question, and I had a reason for that. Remember. Well, because of the dimension, because we want to have a wait. Well, because I guess because there is now everything is computed independently for each word. Let me think. Or I think it's because of the dimension, right? You want to project it back to the fixed dimension, to the dimension of the. Maybe it's here. Let me see if I have the formula.
Maybe you want to combine information from different dimensions. Otherwise,
yes,
each dimension is still separate, right?
It's to right. It's to take into it's to take into account the interaction between the different features, between the different dimensions, right? And then do the non-linearity there, which because attention doesn't have any non-linearity, that was said before, right? So with the feed forward, you can finally take that into account. And remember that attention is always doing the things pairwise, is always looking pairwise at a word and another word.
There was another question.
Yeah, coming back to the positional encoding layer, I still I understand that you are generating an embedding and then you're just transforming it in order to give a representation, adding a tag of which position of the word you have. But that also generates a different representation in the vectoral space. That in the vector space,
yes.
when you embed it,
yes.
that means that the word machine in position 1 and in position 5 will have a different representation,
yes.
even if it's just like shifting it in the
yes.
space. But when you send it through the layers of the whole machinery, they will be treated in a different way. So I still cannot grasp the way that this actually is just like putting a tag into the...
No.
And how are they being used in order to correctly represent... What I still feel that the grasping of this concept is still not very clear to me.
It's also difficult for me to...
Together with the fact that when you are in the output, you also have a positional encoding layer.
Yes.
But that's only during training or also during
also during testing, because yeah, for the same reason, right? You will do attention, so the same word could appear in the target at position 1, but also 4, and you want to treat them differently. In particular, you want to, you want to treat them differently relative to the position that you are now translating. You see what I mean? So if you are translating, there could be other reasons why you need a positional embedding there, but one that I can come up with is you are translating word 10, and you have the, well, it's not a nice example, but you have a word that appears at position 1, and then you have a word at position 2, 3, and 9. You want, I guess, a way to learn that the closer position should be paid more attention to in general. For instance, if you don't have the positional embedding, you cannot do that. You simply cannot do that because it's a bag of words, really.
Yeah, but it's still a bag of words somehow, because the representation for every word, one specific word in different positions will output a vector that will be treated differently by the whole architecture. So I don't understand where is the... Yeah, we know that it's just shifting it in space for the same representation.
Yeah.
But nevertheless, if they were also trying things like just randomly initializing these positional encodings,
yeah,
I still don't understand why it's not a bag of words, because every vector has a different representation. So in the vector space, this is a bag of words. That's why I still don't understand.
But the fact that the same word can get, as a result of the adding a positional embedding, the same word can get 2 different representations. So it's not a bag of words anymore, because it is order sensitive on some way, right? It is. It's not taken from the embedding matrix as is.
Yeah, I guess.
And the attention can use this information to do something with it. So it can do a different attention depending on this positional information, and it will.
But at which point is that the model actually, like if you, during training, if you send 2 sentences that have the same word in different position, the word machine in position 1 and the word machine in position 10, at which point will the model know that these 2 vectors, when sending it to the encoder and the decoder, are representing the same word? There are just 2 vectors that they have a different representation.
But they will have a lot of similarity, because it's one component of the sums. Well, right? It's one of the addendum, so they will have a lot of similarity. I don't think this adding the positional encoding is going to transform it completely. But
no, we see it in the picture, right? Like it's
which
not
one? This one?
That one, no? I guess. Well.
I think we should take this offline.
Can I be this horrible guy that says, let's stop here because we have a few more
yes,
things to
yes.
say.
Actually, many more, but we will skip them. Anyway, this was it for Transformer. This is a picture that I taken from a very good blog post. I have also the links at the end. So it's yet another view to see everything together. So what can we say quickly about what have we gained with Transformer? It's much more parallelizable, so an empirical, concrete advantage. It has lower complexity, as in less number of computations per layer, and the shorter path among any input position. So long dependencies, in principle at least, are easier to capture. Also, what I think is important to realize is how these two architectures came to existence. So RNNs have a very long history, especially LSTM. They are cognitively inspired, and they were used by scientists also to have a model of memory constraints in the brain. Whereas the transformer is really the result of a lot of clever engineering and brute force architecture search. So really they have tried a lot of different configurations to find that this was good. And does it matter for machine translation quality? Maybe not. And actually it seems that transformer works really better in a lot of different scenarios where it has been tried. But there are abilities of models. There are some properties that you would like these models to have that might actually be in a recurrent neural network, and one of them is actually to model hierarchy in the input. So I leave it there because we don't have much time, and I would just say something about interpretability. So this is the matrix that we have seen back in the RNN-based S2SEG. We had one matrix for each pair of source target sentence, and that was pretty nice because we could kind of understand what was going on, and now that's what we have. And keep in mind, one of the promised advantages of transformer, at first what it is more interpretable. So you have 6 times 8 of these guys for the same pair of sentences, and now they are actually being cherry-picked and shown differently, but really that's what you have. You have 6 times 8 this attention, which you could also represent as matrices, but really how can you really interpret that? So that is not to say that we shouldn't use this model, but interpretability is still a big issue in this type of models. So we have 5 minutes more, and maybe I could leave the choice to you. Shall we talk about neural MT inference? That's a very brief slide. We have another slide on word segmentation, and we have 3-4 slides about evaluation in MT and some open issues. So let's say between decoding, word segmentation, and evaluation, which one? Voting, which one do you want to? Sorry? This one? Yeah, okay. Not evaluation. All right. So it turns out that inference or translation can be done with a rather simple beam search procedure. It's usually sufficient to produce high-quality translation. So basically what you do is you set a beam size, for instance 5, and if you remember the older slide where we had the distribution and then we had the sampling, we are going to pick the 5 best, the 5 words that have the highest probability there, and we are going to use it as a suffix of what we have produced so far, and then we keep this in memory, the 5 best translations, and then each time step we revise this, we have the complete probability of each subsequence, and we are always keeping in memory the 5 best hypotheses, partial hypothesis to this point. There is a nice tool for visualizing beam search, by the way, in OpenNMT, so that's something you can use to understand in practice how this works. So this works better than greedy decoding in practice. However, it's interesting that larger beam, much larger beam than 5, doesn't mean better result in general. So I know there's a lot of work also to improve this procedure. Sorry if I'm not mentioning that. But yeah, still what I find interesting is that we came from SMT where you had to explore a huge space of translation to get things of a certain quality, and now with the simple beam size of 5 you get pretty good stuff there. And I guess one of the reasons the model is very confident in its predictions, so even if you explore much more of its space, there is not something substantially better would pop out. Word segmentation, so yeah, it's important to keep in mind that when you train on real-world data, you could have arbitrarily large vocabularies, and that's going to be a problem for training these models, because that means very large matrices and set of weights. So you definitely need a way to fix the size of the vocabulary. Early neural MT models were trained at the level of words, meaning token space, the space delimited tokens in the languages where you have the space, or the blank delimited tokens, I should have said. And the vocabulary was then simply limited at the top and frequent words, so that seemed to make sense. And everything that didn't fit to this vocabulary at train or test time would be mapped to an unknown tag, which would also be treated as any other word by the model. So you would have this catch-all category of words that the model learns to use during training and also to generate at output. So actually back then you could have translation that contain a lot of unknowns. When the model didn't know what to do, it could just start producing unk. And of course there are some kind of workarounds this. Maybe you're going to see one in the lab. So you can actually, instead of generated unk, you could use some kind of alignment and plug in the word which you believe should be actually the translation there. So it's really a kind of post-processing step. But you can do different things. So for instance, in some languages, just limiting to the top and frequent words will not really work, because you have a lot of morphological phenomena, for instance. And then if you model things at the level of word, you are completely ignoring all the similarities between words that share, for instance, the same root form. So character level neural MT, a lot of work has been done there, it's still being done, tries to address this problem. It's suitable for morphologically rich languages. However, it has a drawback that if you segment the sentence at the level of characters, the sequences will become very longer, and it will be also difficult to capture dependencies among them. And that's why hybrid character word modeling strategies have been proposed, but these are typically complex and expensive. The intuition behind there is that basically every time you encounter a new word, you are going to have to build its representation all the way down from its characters. And that's definitely more expensive than just looking up a word embedding matrix. A practical compromise is subword segmentation. Simple data-driven segmentation models like byte pair encoding and sentence piece work quite well in this sense, and they are based on a very simple idea there, that you just look at frequencies of words in the corpus, and you are going to keep words as is if they are frequent. Otherwise, you're going to segment them down to smaller and smaller pieces, down to the level of characters. New words can always be segmented using these methods. So you can do open vocabulary translation. You don't need to map anything to unknown. In the worst case, you will split a word that you have never seen at the level of characters, and the model will try to come up with a representation of that. This is an example from Sanrik's paper about byte pair encoding, where I just put it here because it's showing what this can be helpful for. This is a long German compound. And interesting, you can also see that the subwords, they are not linguistically meaningful in any way. But that's okay, because the interaction between neighboring words is taken care of by the model somehow. So it's much less important than it used to be with pre-neural models. So I think I will skip evaluation, because it's definitely time for lunch, and maybe just conclude with, although I should say, do give some attention to evaluation when you do your experiments, because it is a big problem, and it also can explain a lot about why things work or don't work. So open issue in MT. So in March 2018, this paper from Microsoft claim human parity on a very difficult language pair, Chinese to English. And that's not just that they thought, oh, we have a great system. They actually used a lot of human evaluator, and they really saw that in most of the cases, these people could not distinguish. Like, I could not distinguish at the beginning of the talk if that website was actually written originally in English or it had been translated. It's true, but it's not that everything is solved. So what is still a problem there? I'm just naming 3-4 points. There are more, and these are maybe the ones that are more interesting to me. So translation quality is still shaky if you consider a wider context than the sentence. So in particular, in this study by Microsoft, they were using an evaluation protocol where the evaluator is, the annotator is only presented with the sentence level translation. And there's so much that you don't capture there. Actually, many things will be difficult to translate for a human too if you don't present the document context. And of course, not only document level, but also larger context about the word or the discourse where this sentence should be translated. It's still very difficult to incorporate that in a neural MT. Also, recent studies reveal biases and lack of systematicity in neural MT. So biases is linked to the fact that, well, there are biases in the data. So there's an interesting study showing that if you translate, you probably have heard this about word embeddings, and it happens in machine translation too. You translate doctor from a word, from a language that doesn't gender, and the pronoun was also gender neutral, then the translation of that pronoun in English is going to be he, most probably, and the nurse is going to be she. So very similar issues of what is being discussed recently about the biases in NLP in general. Lack of systematicity is something different. It's basically something that people are starting to notice, that sometimes neural MT breaks with no specific reason. So you have a sentence that is translated very well. You change the tense or you change the person of that sentence, and suddenly it cannot translate it. And then it gets very difficult to understand why it is breaking. And this is also related to the fact that neural MT is very data hungry. So if you do have a lot of data, it's going to work really well. Otherwise, you have to really be clever in how you model things. And dealing with rich vocabularies, morphologically rich languages, is still very hard. New or exacerbated issues in neural MT are how to make use of large monolingual data. So that used to be, the language model used to be a natural component of the SMT formulation, whereas in neural MT, the P of E is not in this formula, so it has to be fused in some way, and there are many ways to do this that have been presented, but still it's just not part of, it's not easy to include it in the end-of-end trained neural machine translation system. So you have things like back translation, dual training are trying to address this problem, because typically you have a lot of data in your target language where you have much less data in your language pair of translations. Learning representations of rare words is a problem. Yeah, interesting enough, rare words used to be less of a problem in SMT actually, because if you have a word that appeared only in 3 sentences in your corpus, chances are that you can also learn, if it was in your corpus, of course, it would be quite easy to just detect its translation in those 3 sentences and use it at test time. Whereas neural models struggle with representing rare events in general. So the rare words will have bad representation, and then you have a cascade of problems starting. If the embedding is bad, you cannot hope to have a very good translation for that word. And finally, poor model interpretability. Definitely, that's what we lost from going from an SMT. It makes it difficult to debug translation errors. And also, practically, it makes it difficult to enhance models with expert knowledge of any kind, which in MT is typical, it could be there. So you could have terminologies, think of domain-specific translation scenarios. You have your own bilingual terminology. How are you going to ask the model to use it, to force it to use that terminology? It's not trivial at all. Or you have some linguistic resources. You have a morphological lexicon. How do you use that to improve the ability of the model to translate that language? And that was it. These slides also include a list of references that I grouped by subtopics here. I hope that's going to be useful for someone that has just started. And this is a set of useful links that I really encourage you to look to get deeper into this. Thanks for your attention.
Okay. Thank you very much. And thanks also for the audience for the very interesting questions, because I think that's exactly what we want. Maybe we gave a little bit of a hard time
Thanks
for
for
Arianna.
your questions.
And Arianna, this is, thank you, on behalf of the organizing committee.